This video discusses work and how it's related to energy. So to start off, we have to talk about conservation of energy. So with conservation of energy, the total energy of a system of objects is constant. However, energy can transfer from one type to another or from object to object. So when work is done, we're really talking about one object applying a force on another, changing that object's energy. However, energy is still conserved because one object is giving energy to another object. So, if you remember, we talked a lot about roller coasters. So at the top of the roller coaster, we're going to have 100% potential energy. Halfway down, it's going to be 50% PE, 50% KE, and at the bottom, it's going to be 100% kinetic energy. Now, no one picked up on the fact that, well, when we get on a roller coaster, it doesn't have energy. When we get on a roller coaster, our total energy is 0 joules. We have no potential because we're at the bottom. We have no kinetic because they stop the ride before you get on it. So, the roller coaster has to gain energy somehow. How do roller coasters gain energy? Well, they have that little motor with the chain attached to it. This chain does work. So, work is done when one object changes the energy of another object. So to go into more detail, let's talk about weightlifting. So if we have a barbell here, we can displace it and pull it up here. To do that, I need to apply a force on it. I need to apply a force equal to mass times gravity, its weight, to lift it up. Well, how high did I lift it up? I lifted it up some distance here. And when we get down to it, work is equal to force times distance. Well, work's also equal to a change in energy. So these two are equivalent because the force I'm using here is mg, the distance is d, but it's also a height. So it's really mg delta h. It's the change in potential energy when I'm lifting it up. If I'm talking about rolling a ball up a ramp, so I start out with my ball, and I want to roll it up a ramp, well, I got to do the same thing. I have to apply a force on my ball to make it move. And I move it up some distance, right? The distance is here. Now this cosine theta comes in because, well, since I'm rolling it up a ramp, the height isn't the distance of the ramp or the displacement of the ramp, but it's d times cosine of theta. So that's why we have that d cosine theta in our formula sometime. So let's say we have a mass of 100 grams, or 100 kilograms rather. G is always going to be 9.8 meters per second squared, and I apply that force over a distance of 2 meters to make it easy. So I'm lifting a 100 kilogram mass from the floor up to above my head. How much work do I do? Well, work is the force times the displacement. The force I have to use is going to be 980 newtons, because it's 100 kilograms times 9.8 times 2 meters gets me 1,960 joules of energy. When I'm talking about changing kinetic energy, it's very similar. There's two ways to do it. We start off with a familiar formula to us, and then one that's unfamiliar. But if you took a college level physics class, you would see this one. So delta V is equal, or delta V squared is equal to 2AD, and what you end up getting is, well, work's changing KE. If I plug in V squared right here, I can just come up with work equals MAD, and Newton's second law says MA is a force. So, to solve one like that, let's say how much work is done accelerating a 2 kilogram ball from rest to 5 meters per second. What we would do, work is going to be delta KE because we're changing its kinetic energy. So work is 1/2 m delta V squared. So 1/2 times 2 is going to be 1. 5 squared is going to be 25. So we end up with 25 joules. Okay, hopefully this is helpful.